Have you ever really stopped to think about what's going on inside your phone? I mean, we are surrounded by these amazing gadgets, right? But they all share this one tiny, fundamental secret. A secret that, if it didn't exist, our entire digital world just wouldn't.
And it all starts with a question you've definitely asked while, tripping over a power cord. Why this thing? Why does every single device we own need this clunky brick to plug into the wall? Well, let's dive in.
Okay, so the power coming out of our wall sockets is something called alternating current, or AC. You can think of it as kind of wild and chaotic, constantly switching its direction back and forth. But our delicate electronics, they need something way calmer, a smooth one-way flow called direct current, or DC. So the big question is, how do you tame that electrical chaos? The answer is a brilliant little electronic gatekeeper called a diode. It's pretty much the unsung hero inside every single one of those power adapters, and its entire job is to control the flow of electricity on a microscopic level. Now, to really understand the diode, we've got to look at the almost magical material it's made from. It's not a conductor, like metal, and it's not an insulator, like plastic. It's something else entirely. Something right in the middle.
So, materials basically fall into three different camps based on how they handle electricity. You've got conductors, like copper and other metals, that let electricity flow super easily. Then you've got insulators that block it almost completely. And then you have this just right category in the middle, semiconductors.
But what really makes them so different? Well, it all boils down to a concept from quantum physics called the energy gap. And don't worry, it's actually a lot more straightforward than it sounds.
Think of it like this. For electricity to flow, these tiny particles called electrons need to get energized and jump up to what's called the conduction band. In a conductor, as you can see, there's basically no gap. The electrons can just hop up with almost zero effort and start moving around. That movement is the electric current.
Now, check out the total opposite. Insulators. Here, that energy gap is a massive chasm. The electrons are totally stuck on the lower level and they just can't make that jump. No moving electrons, no current. Electricity is completely blocked. Simple as that.
And this is where our Goldilocks material comes in. A semiconductor has this small, manageable gap. By itself, it doesn't really conduct that well. But that small gap is the secret. It means we can actually persuade the electrons to make the jump. It's controllable.
So, a pure semiconductor is controllable, but on its own, it isn't all that useful. The real breakthrough, the game changer, came when scientists figured out they could actually hack it by adding tiny, specific impurities. This process is basically the secret sauce of all modern electronics.
It's called doping, and it is incredibly precise. We're talking about adding just 1 or 2 impurity atoms for every million semiconductor atoms. It's almost nothing. But that tiny, tiny change has this massive effect on how it behaves with electricity.
Now, doping comes in 2 main flavors. First, you can add an impurity that brings in extra free-roaming electrons. Since electrons are negative, we call this N-type. Simple. Or you can add an impurity that creates a vacancy, a spot where an electron should be. We call this empty spot a hole, and since it's a space that's waiting for a negative electron, it basically acts like a positive charge, and we call that P-type.
So now we have these 2 customized materials. N-type, which has extra electrons, and P-type with extra holes. Neither one is all that special by itself, but something truly incredible happens when you bring them together. You create what's called a p-n junction, and this simple interface, this meeting point between P-type and N-type material, that's the heart of the diode. This is where all the magic really happens. The second they meet, the free electrons from the N side just rush over to fill in the holes on the P side. They combine, they neutralize each other, and they create this thin barrier right in the middle called the depletion region. Inside this zone, there are no free charges left, so it acts like an electrical wall. And this little wall, this is what gives the p-n junction its superpower. A superpower that has pretty much defined the last 70 years of technology. It turns the flow of electricity into a one-way street. So here's how it works. If you apply a voltage in one direction, what we call forward bias, it pushes the electrons and holes towards each other. This shrinks that wall and lets the current flow right through. But if you apply the voltage in the opposite direction, reverse bias, it pulls the electrons and holes away from the junction. This makes that wall even bigger and stronger, and it blocks the current completely. You can see the mechanism perfectly right here. In forward bias, the path is clear. Resistance is super low, everything flows. But in reverse bias, that depletion region gets wider. Resistance shoots way up, and the flow just stops. It's a perfect one-way switch.
I mean, the source material puts it perfectly. Current flows only in forward bias. In other words, it's a one-way street for electricity. That is the entire trick. A one-way gate.
Okay, let's bring this all the way back around. How does this amazing one-way gate solve the problem of our power brick? How does it get us from that wild AC to the calm DC we need?
Remember that chaotic AC wave from the wall, flipping back and forth between positive and negative? Well, the diode just acts like a bouncer. When the wave is positive, the gate's open and current flows. But the second that wave tries to flip to negative, the gate slams shut. It just blocks that entire half of the wave. And the result? A current that only flows in one direction. We've tamed the chaos and created the smooth DC power our gadgets need to survive.
And honestly, converting AC to DC is just the beginning. It's just the tip of the iceberg. This exact same PN junction is the core of so much more. The screen you're watching this on? Probably lit by light-emitting diodes, LEDs. Solar cells? They use a PN junction to turn sunlight into electricity. And if you sandwich these layers together, you create a transistor, the tiny little switch that's the brain inside every single computer chip on the planet.
It's incredible when you think about it. This simple one-way gate, all born from cleverly hacking a Goldilocks material, is the foundation for everything from a tiny calculator to artificial intelligence. It really makes you wonder, what are we going to build with it next?